Question number 1, we have a cyclic quadrilateral. Remember, in a cyclic quadrilateral, opposite angles are supplementary. It works a little bit different than the regular parallelograms, squares, rectangles, rhombuses that we've been seeing where opposite angles are congruent. In cyclic quadrilaterals, that means quadrilaterals inscribed in a circle, the opposite angles are supplementary to each other. So all I need to do is take a pair of opposite angles since they all use x, all the angles, and I just need to make an equation that says if I put the opposite angles together, I get 180 degrees. (180 minus 15 is 165). Oops. Divided by 3 is 55. Notice how 55 is the answer choice? Make sure that you plug in. So I'm going to plug in here because I'm looking for angle D. So I want to know what B is. So 55 minus 10 is 45. And then D is supplementary with B. So 180 minus 45 is 135. So angle D is 135 degrees. For number 2, we need to find the equation of the circle. So I need the center and the radius. The center I can see because it's labeled O, center O. So that's -1, -2, -3, -4, 1, 2. -4, 2 is the center. So that means answer choice 1 and 2 are out because that has a center of 0, 0. Unfortunately, it doesn't help me narrow down between 3 and 4 because 3 and 4 both have the center of -4, 2. The radius is what's different. So I have to find what the radius is. So be careful here because we don't have clear points over here. So I can't just count from the center to the radius because I don't know if this is halfway. I don't know if this is like 0.75 of the way, somewhere in between, right? I don't know where this point is. So what I'm actually going to do is I'm actually going to have to take a clear point and let me try to find one. There. Oops. Too hard on the computer to make a line. And I'm going to have to find the length of this radius. And since this is not a straight vertical or horizontal line, I'm going to have to use distance formula because I can't just count the boxes. Or you can use Pythagorean theorem, whichever one you'd like, if you just turn this into a right triangle over here. But this is the point, -1, -2, -3, -4, -5, -6. 1, 2, 3, 4, 5, 6. So that's the point, -6, 6. So I'm going to use distance formula, but once again, you can use Pythagorean theorem, just connect this into a right triangle and find the length of the hypotenuse, and that works as well. But I'm going to use distance formula. So distance formula is x2 minus x1 squared plus y2 minus y1 squared. So let me do the x's first. So I'm going to do -4 minus -6. And then let me do the y's. I'm going to do the same order, 2 minus 6, be consistent. Okay, so this is +2 squared, which is 4. And let me bring down the radical. You don't want to forget the radical. And that's -4 squared is 16. So that's radical 20. And if I simplify radical 20, that simplifies into radical 4 and radical 5, which is 2 radical 5 because radical 4 is 2. And if you didn't know how to simplify radicals, that's okay. Just recognize 20 is not the same thing as radical 20. Those are two different numbers, and that would help you make your selection there. Okay. Number 3. What is the length of BC? So since we have tangents to the circle at the radius, when a tangent and the radius meet, they're perpendicular, which means they form right angles. We also have congruent vertical angles. So what we have here is triangles that are similar by AA. When you have similar triangles, you can make a proportion involving the corresponding sides. So I'm going to make a proportion to find BC. I'll do from the small triangle, and then on the other side, I'll do the corresponding sides from the big triangle. And then I'll cross multiply. And then the only thing I have to do from here is just divide 50 by 4. And we have x is equal to 12.5. And that's our answer because we labeled BC as x. So that is our answer. Okay, what we need to recognize for this next one is that tangents from the same point to the same circle are congruent. So AT and ET are both tangent to circle Y and come out of point T, so they're congruent. CT and ST are both tangent to circle X and they come out of the same point T, so the whole segments are congruent to each other. They tell us the ratio of TA to AC is 1 to 3. So TA is the one part, so I can represent that as 1x or simply just x. And AC is the 3 part, so I can represent that as 3x. So that means 3x plus x, the entirety here is 4x of the segment. And we need to find the length of SE. Well, what we can do is we can find x and we can plug in. Because if these holes are congruent and these pieces are congruent, then these pieces have to be congruent as well to each other. So we can just find x and we can just plug in over here. They do tell us that TS is 24, so that means that 4x is 24 because the whole segment's 4x. So 4x is 24. And if I do 24 divided by 4, that gives me 6. And then if I plug in, 6 times 3 is 18. So AC is equal to 18. And that makes sense because that's the 3x part. It's longer than the x part, so it should be bigger than the x part. Okay. In the next one over here, we have a radius and a tangent that meet, so they're perpendicular, which means that they form a 90-degree angle. BA is 15, and OB is 17. And we need to find the measure of the radius. So we are finding this side over here of the triangle. So we can use Pythagorean theorem because we already know 2 sides of the right triangle. And we want to find the last side. So I'm going to do that over here. I'm going to do x squared plus 15 squared equals to 17 squared. Make sure that you do put 17 in for C as it is the hypotenuse of that right triangle. So we have x squared plus 225 equals to 289. I'm going to subtract 225 from 289, and I have x squared is 64. And if I take the square root of both sides, I have that x is equal to 8. And the radius is represented as x, so that is 8. So the radius is 8. Okay, this question is which expression represents the arc length of AB? Okay, so in order to find the arc length, I need to find the circumference of the whole circle. And then I need to find the part of the circumference that this represents over here. So the circumference of the whole circle is pi times diameter, and the radius here is 6. So the circumference here would be 12 pi. And then to find the part of the circle, I can do the central angle measure over 360, and that will give me the part of the whole circle that this sector is. And then I can simply just multiply that by the circumference. And if I simplify 120 divided by 360 in my calculator, and you can hit math, enter, enter in order to convert it into a fraction, you should see that 120 divided by 360 is 1/3. So that is this answer choice over here. So you don't actually have to go any further with the solving. That's that answer choice. And over here we have the incenter. And the incenter means that it's where the angle bisectors meet. So that tells me that the segment is bisecting angle C. So it's cut into 2 equal parts. That tells me the segment is bisecting angle F. So it's cut into 2 equal parts. And that tells me the segment is bisecting angle E. So it's cut into 2 equal parts. Once again, the incenter is where the angle bisectors meet. We do have to know these words: incenter, circumcenter, centroid, and orthocenter. Okay, we know that angle FEC. So this whole angle over here is 84 degrees. And since I now know it's being split equally in half, 84 divided by 2 is 42. So we have 42 and 42. Sorry for my terrible writing over here on the computer. Let me try that again. Okay, much better. And we're told angle ECF is 28. So this whole angle is 28. So that means each piece is 14. I don't know if we need this. I didn't really look at the question yet. And determine and state angle BRC. So we're looking for this angle over here in green. Okay. So if this angle was 84 and this angle was 28, I know that all 3 angles of a triangle make 180 degrees. So 84 plus 28 equals to 112. And then if we do 180 minus 112, we have 68. So angle F, the whole angle here is 68. And that means each half is 34. Now what I want to do is I want to focus on a triangle that could be helpful to me because this diagram is split into multiple triangles. And I want to find angle BRC. So for me, I feel like this triangle is going to be the most helpful because I already have the 42-degree angle. I already have this whole 28-degree angle, and I'm looking for the last angle of that triangle. So let me do 42 plus 28 and see what that is. And that is 70. And then I can do 180 minus 70, which is 110. And that is the angle measurement that we're looking for. Okay, moving along. Over here, we are dealing with arc length again. It says an arc with a length of 2 pi, and we're solving for angle B in radians. I'm going to use our arc length formula for when we have radians, S equals R times theta. And remember, S represents the arc length, which we're given. It's 2 pi. We have the radius, which is 10, and we're solving for the angle. Remember, this formula can only be used when you are working with radians. So all I need to do is just divide both sides by 10. So 2 over 10 reduces to 1/5. So 1/5 pi, or you can simply just write it as pi over 5. You can also do it with our regular arc length formula. Our length equals to the angle over, instead of using 360, you would use 2 pi, because that's the equivalent of 360 in radians, times the circumference. So the arc length is 2 pi. You're solving for the angle, and your circumference would be 20 pi. Let me first clean up the right-hand side and multiply the fractions across. So that would be 20 pi theta over 2 pi. Let me stick this over 1, and then I can cross multiply. I'm going to continue on to this side. That's 4 pi squared. That's a 4. 4 pi squared equals to 20 pi theta. From here, I can just divide both sides by 20 pi. And 4 over 20 reduces to 1/5. Pi squared, take away a pi is just pi. So that is the same thing, 1/5 pi or pi over 5. See how the formula S equals R times theta is so much less work when you're working with radians. So it's a very useful formula, but it's only for radians and only for arc length. Okay, over here we have another arc length question, and this time we're working with degrees. So I'm going to use our regular formula because if I use this one, I'm going to have to convert my angle to degrees afterwards, which you can do. You can just multiply it by 180 over pi to convert. But I'm going to use our regular formula. So arc length, and I wrote it on the other side, so I'm not going to rewrite it. The other side of the screen over here equals to the angle, which I'm finding, and we're doing degrees, so 360, times the diameter. So the diameter would be the radius times 2. 4.5 times 2 is 9, so that would be 9 pi. And, oh, it tells us the arc length. I'm like, we have to know what the arc length is here because we can't have two unknowns. The arc length is 6.2. So over here, I'm just going to solve, and I'm just going to multiply my fraction across. 6.2 equals to 9 pi theta over 360. And then I could just simply put this over 1, and I can cross multiply. So I have 9 pi theta, when I multiply this way, is equal to, let me multiply this way. I have to do 360. 360 times 6.2. And I got this. And then dividing by 9 pi. I had to get the actual calculator out for this. 2,232 divided by 9 pi. And that's about 78.9. Was that an answer choice? Let's check it out. Yes, about 79 degrees. And there we have it. Okay. Number 10. Chord DC is parallel to chord BA. When we have parallel chords, the arcs in between them, the arcs that they intercept, touching D, touching B, arc they intercept, touching C, touching A, arc it intercepts. So the arc between them, the arcs that they touch, that they intercept, are congruent to each other, and it's the arcs between them. So angle BCD is 30 degrees. That's an inscribed angle. That makes this arc 60. This arc's congruent to it. That makes this arc 60. We need AOB. I see AOC, since it's a central angle that opens up to this arc, would be 60 degrees. And these are supplementary, so 180 minus 60 equals to 120 degrees. And that's the answer. This next one over here is sector area. It says find the area of the shaded sector. So be careful. We're not using 70 degrees. We need the central angle that opens up to the shaded sector. So if this is an inscribed angle that's 70, that means that the arc is 140 degrees, and that means that the central angle is also 140 degrees. So now let's find the area of the sector. So sector area of the sector is equal to the angle over 360 times the area, because we're dealing with areas for sector area. So sector area equals to 140 over 360 times, and the radius is 9. 9 squared is 81 times 81 pi. I'm going to put this into the calculator. I'm not going to put the pi in because it does not want me to put the pi in. So 140 times 81 Okay, and then I'm dividing by 360. Oops. Oh. Oh, that's not what I wanted to press. Okay. 140, I hate this calculator, times 8. That's what I wanted to press. And then this divided by 360. I'm always forgetting how to use this. We should convert it to a fraction. If you have a graphing calculator, you can convert it to a fraction pretty easily. I'm going to use my graphing calculator right now to convert it to a fraction. Uh-oh, I did times 8, not times 81. That's why my answer is off. Let's start again with the multiplying. 140 times 81. Okay. And then the answer divided by 360, because I realized the answer choices were in decimals and 31.5. I'm like, why is mine not matching up? And that's 31.5 pi. Okay. For this next one over here, we know that the length of CA is 12.5. We know that the length of CB is 4.5, and we need to find the length of DA. So we're dealing with the lengths of outside segments, and remember, to find lengths of outside segments, it's whole times outside of one outside segment equals to whole times outside of the other outside segment. Let's start with the secant. The whole of the secant is 12.5. The outside part is 12.5 minus 4.5, which is 8. That's the part that's outside the circle. For the tangent, the whole is x, we're looking for it, and the whole tangent is completely outside the circle. So the outside part is also x, and that always happens when you have a tangent. So 12.5 times 8 is 100. So 100 equals to x squared, so x is equal to 10. So the length of DA, which is represented as x, is simply just 10. A toy truck is located within a circular play area. Alex and Dominic are sitting on opposite sides of a cord that contains the truck. So I'll just put the truck in a red dot over here. Alex is 4 feet, I'll label it T. Alex is 4 feet from the truck, and Dominic is 3 feet from the truck. Mira and Tamara are sitting on opposite endpoints of another cord containing the truck. Mira is 8 feet from the truck, and Tamara is what we're looking for. We're looking for how far Tamara is from the truck. Okay, so what we have here is we have lengths of segments inside the circle, intersecting chord segment lengths. Notice how the segments are inside the circle, they're chords, and we're finding the lengths, or we have the lengths and we're finding lengths. So we're going to use our theorem for that, which is part times part of one chord equals to part times part of the other chord. And we measure the part from the endpoint to where the chords intersect. So I'm going to start with the blue chord. So from one endpoint to the truck, it's 4. From the other endpoint to the truck is 3. Now I'm going to do the green segment. From one endpoint to the truck is 8. From the other endpoint to the truck is what we're trying to find. So we have 12 equals to 8x. Not going to work out nicely, but it does say round your answer to the nearest 10, so it's not supposed to. So I'm going to do 12 divided by 8, and it worked out kind of nice. It is 1.5 feet, not too crazy. Okay, over here we have a proof. So over here, oops, we want to make sure that we mark our diagram with the given information before we even write up our proof. So we have that AD is parallel to chord BC. And what we're proving is that BE is congruent to CE. So already from the proof statement, I recognize that this is going to be CP/CTC because we're proving segments congruent. So when we're proving segments or angles to be congruent, we generally prove triangles congruent first, and then we could CP/CTC other sides or angles of those triangles, because once the triangles are congruent, all the other stuff about them automatically becomes congruent because the whole triangles themselves are congruent, and that's CP/CTC. So this is going to be a congruent triangle proof. So our plan is to prove triangles congruent first, and then we could CP/CTC what we need. It's not a similarity proof because we're not proving triangles similar. The proof statement doesn't say that. We're not proving a proportion. The proof statement is not a proportion. We're not proving a product. The proof statement is not a product. The proof statement is a congruent statement. So this is going to be a CP/CTC proof. Congruent triangle proofs are annoying because you don't know how you're going to prove them congruent, right? It could either be SSS, it could be SAS, it could be AAS, it could be ASA, it could be HL if you have right triangles and you have congruent hypotenuses and congruent legs. So it could be any of these choices. It can't be ASS, so don't write that. That is not a valid way of proving triangles congruent. And remember, AA is not a way of proving triangles congruent. AA is only for similarity. So first I want to identify what triangles I need to focus on. Ultimately, I need BE and CE. So I need to identify triangles that have BE and CE as its sides. So for me, I'm going to use these because they have BE and CE as its sides. So if I could prove those two triangles congruent, I could just easily CP/CTC BE and CE. And already I see vertical angles, which is really nice. I'm also noticing something else. I don't know if it'll be helpful to me, but let's try it. And then I can always erase it if not. So we have parallel chords. So remember the arcs in between them are congruent. So that would make these sides congruent because congruent chords intercept congruent arcs. If these chords are touching congruent arcs, then that means that they're congruent to each other. Once again, congruent chords intercept congruent arcs. So I don't know if that'll help, but that gives me some stuff I could use here. I also notice that I have inscribed angles that intercept a semicircle or a diameter. And we know from test one and doing a bunch of proofs like this, that creates right angles because these are half the arc. If the intercepted arc is 180, then these are both 90 degrees. And oh, I have AAS. So I'm going to use AAS. There might be other ways to do this proof. That's the way I saw. So I'm going to use AAS. And then I'm going to just CP/CTC what I need. So that's all we're going to do. And now that we have our plan, all we have to do is simply just transfer what we marked in the diagram in our plan and transfer it into our proof. And that's why it's really important to make a plan first. Otherwise, you're going to go aimlessly in circles and put things that are irrelevant or maybe even incorrect and wind up losing points. When if you just make a plan first, then you could know what you're doing. Okay, so I wrote the givens already, and now I'm just going to transfer from my proof, from the markings in my diagram to my proof. So I'll start in the order that we did it. So I'll start with arc AB. Remember your symbols being congruent to arc CD. And our reason from that was due to the parallel chords. Parallel chords intercept congruent arcs. And from that, we were able to say that the sides that we needed, segment AB and segment CD, are congruent. The sound notation is very important. We were talking about arcs, and now we're talking about the segments, two separate things. Congruent chords intercept congruent arcs. Okay, now I'm going to put in the vertical angles. Angle BEA is congruent to angle CED. Technically, it is not correct to write vertical angles are always congruent. Then you would need a step stating how you know that you have vertical angles. Vertical angles are formed from intersecting lines. So technically, you do have to write intersecting lines form congruent vertical angles. And we don't want to give anybody a reason to take off points for something that we know on the Regents exam. Then I'm going to say angle, oops. Yeah, I can't call that angle B. I meant to write angle ABE and angle DCE are right angles inscribed angles that intercept. You can say a semicircle or a diameter. A semicircle are right angles. And then we do just need to say that they're congruent because we're using AS and we're using the right angles as one of our congruent angle pairs. So then I'm just going to say angle ABE is congruent to angle DCE. And I'm going to put here all right angles are congruent. And so now in our proof, we have the S that we were using for angle side. We have one of the A's that we were using for angle side. And now we have our last A that we were using for angle side. So everything we need is in here. We can now say that the triangles are congruent.